Hi ladies, chapter 24 is over comparing means. It's very similar to the two proportion z-test, but using the t-test instead, so it's not too different from that. Okay, so the first thing you want to do is plot your data, and you all remember back when we did box and whisker plots to compare quantitative data. We want to do the same here. So the natural display for comparing two groups is box plots of the data for the two groups placed side by side. You might remember doing this to compare two different groups. Remember the mean, you can see the medians and the interquartile ranges, and also remember the fences go out to the minimum and maximum points if they lie within the whiskers. So, all right, once we have examined the side-by-side box plots, we can turn to the comparison of two means. Comparing two means is not very different from comparing two proportions, like I said a moment ago. This time the parameter of interest is the difference between the two means, mu1 minus mu2, instead of p1 minus p2. So remember, for independent random quantities, variances are added. All right, so this was back whenever we were discussing probabilities and means and standard deviations in chapter 18, I believe, when the central limit theorem was introduced. Anytime you're looking at the variance or the standard deviation of differences, remember you take the square root of them and then add them together. Add the squares of them together. So remember, we still do not know the true standard deviations of the two groups, so we will need to estimate and use the standard error. Okay, so this is why we're using the t-test, is because we do not know the population standard deviation, sigma. Okay, so here is our standard error formula. The square root of your sample standard deviation squared over n1 plus the sample standard deviation squared over n2. Okay, here's a comparison of what we learned so far, and these are also the formulas that are on the AP Stat exam. So remember, for single samples, the sample mean, the statistic is the sample mean, and the standard deviation is central limit theorem. You use sigma over square root of n. Here's sample proportion information. And on the two sample down here, this is what we're doing today, difference of sample means. This is the standard error here, okay, because we do not know the population standard deviations. Okay, and this is a special case. We have not talked about this yet in class, and we will soon, but don't worry about this right now. Okay, so a difference of sample proportions is what we did last chapter in chapter 22 with two proportions. Okay, so we're focusing on this right now. Okay, the difference of sample means. Okay, so because we're working with means and estimating the standard error of their difference using the data, we shouldn't be surprised that the sampling model is a student's t-test. Okay, very similar to what we did last chapter, just now we're looking at two means. So the confidence interval we build is called a two-sample t-interval for the difference in means, and the corresponding hypothesis test is called a two-sample t-test. So the assumptions and conditions are the same. We have to make sure they're independent. Make sure everything is satisfied with the randomization condition. So were the data collected with suitable randomization? Make sure the 10% condition passed. So we don't usually check this condition for differences of means. We will check it we'll check it for the means only if we have a very small population or an extremely large sample. And remember, we have to check that everything is nearly normal. And to do that, you can graph a histogram of them. Or on the box and whisker plot, you could tell it's normal as well if the spread is the same on both sides. Okay. Okay, so when the conditions are met, the standardized sample difference between the means of two independent groups can be modeled by a student's t-model with a number of degrees of freedom found with this special formula. Okay, this is your degrees of freedom formula. This is crazy now. It's no longer just n minus 1, right? Okay, so when the conditions are met, we are ready to find the confidence intervals for the difference between means of two independent groups. Difference between means of two independent groups, mu1 minus mu2. The confidence interval is your sample mean of the first group minus the sample mean of the second group, plus or minus your critical value, the t critical value, times your standard error of x1 minus x2. And remember, I showed you the standard error formula before here. Okay? So confidence interval is the same as it always has been. It's your mean plus or minus critical value times standard error. Okay, with the special formula for the degrees of freedom. All right, so the special formula for the degrees of freedom for our critical value is a booger bear. Here it is. You do not have to remember this. You can use your calculator. So this is because of this, we'll let technology calculate degrees of freedom for us. There's no sense in memorizing this formula. Please do not memorize it. The calculator will do it for you. Okay, and so always we want to use the smaller of the N1 or N2 minus ones. Okay, so this is more conservative estimate of the true degrees of freedom. So always use the smaller sample size for your degrees of freedom. So since we're comparing two groups. Okay, two sample t-test. We test hypotheses that the null hypothesis that mu1 minus mu2 is equal to to 0. Okay, where the hypothesis difference delta. I don't know if you've all taken physics or chemistry. Remember, delta is change. So basically, you're saying that the difference between the two is 0 using the test statistic t. Remember, our t-score is going to be x1, our sample mean 1 minus the sample mean 2 minus the delta of 0, which is the change of the null, okay, which is almost always 0 over your standard error. Okay, so again, it follows the same rule of thumb for the z-score and the t-score. You do your sample mean minus your null hypothesis over the standard error. So when the conditions are met and the null hypothesis is true, the statistic can be closely modeled by a student's t-model with a number of degrees of freedom given by a special formula. We use that model to obtain our p-value. Okay, here's the notation for a two-sample t-test. You can either say mu1 is equal to mu2 or mu1 minus mu2 is equal to 0. You do not have to write delta not, okay? You can use 0. Okay, our alternative is either going to be that mu1 is less than mu2, mu1 is greater than mu2, or mu1 is not equal to mu2. Okay, same as was with proportions. All right, remember it's always good practice to, instead of using 1s and 2s, to actually denote what is being used and what you're comparing. Like if you're comparing men against women, make the 1 M and make the 2 a W. If you're comparing years, make the 1 like 1997 and the 2 2007, whatever you're comparing. So that way you understand later whenever we make your conclusion what your null hypothesis was and you don't forget that. Okay, and remember your p-value is always going to be that your population T is greater than your sample, or the population T is less than your sample. Or if it's two-tailed, you won't do 2 times that probability. I don't know. I said population, guys. I'm sorry. My children are downstairs screaming, so I don't know if you can hear that. It's kind of wild in her house right now. Okay, so to pool or not to pool. So you remember when we did the proportions, we always pooled, okay, whenever we did a 2-proportion test. So remember that we, when we know a proportion, we always, we also know the standard deviation. I'm sorry, I'm getting, like, they're seriously screaming downstairs. It's insane. Okay, so remember that when we know a proportion, we also know its standard deviation. So when testing the null hypothesis that 2 proportions were equal, we could assume their variances were equal as well. This led us to pool our data for the hypothesis test. For means, there is also a pooled t-test. Like the 2-proportion z-test, this test assumes that the variances in the groups are equal, but be careful, there is no link between a mean and its standard deviation. If we are willing to assume that the variances of 2 means are equal, we can pool the data from the 2 groups to estimate the common variance and make the degrees of freedom formula much simpler. We would still be estimating the pooled standard deviation from the data, so we use student's t-model, and the test is called a pooled t-test for the difference between means. Okay, so there's a whole section in your book that discusses all of this information, but you do not have to pool, okay? So when should you use pooled t methods rather than 2 sample t methods? Never. Well, hardly ever. Okay, so it's because the advantages of pooling are small, and you're allowed to pool only rarely when the equal variance assumption is met. Don't pool. So it's not wrong to pool with t. It's not wrong not to pool with t-test. So do not pool with t-test. I don't even go into showing you the formula in this slide because it's pretty intensive. So do not worry about pooling with t-test. You only need to pool when you're comparing proportions with the z-tests. Okay, so is there ever a time when assuming equal variances makes sense? So this is for those of you who are interested in what I said up here when the equal variance assumption is met. So is there ever a time when assuming equal variances makes sense? Yes, in a randomized comparative experiment, we start by assigning our experimental units to treatments at random. Each treatment group therefore begins with the same population variance. In this case, assuming the variances are equal is still an assumption, and there are conditions that need to be checked, but at least it's a plausible assumption, okay? Because we're pulling from the exact same population and then randomizing into the experiment, okay? But anyway, so point being, you do not have to pull with t-tests. So there's all that fun stuff for you. All right, so what can go wrong? Watch out for paired data. The independent group's assumption deserves special attention. If the samples are not independent, you can't use two sample methods. Also, look at the plots. Okay, so check for outliers and non-normal distributions by making and examining your box plots. Okay, so what have you learned? We've learned to use statistical inference to compare the means of two independent groups. We use t-models for the methods in this chapter. It is still important to check conditions to see if our assumptions are reasonable. The standard error for the difference in sample means depends on believing that our data come from independent groups, but pooling is not the best choice here. So once again, we've seen we can add variances, okay? What I'm talking about here is when you find the standard error of the difference of two means, you end up adding them. Remember, you do the square root of s1 squared over n1 plus you add it to the this s2 squared over n2. So the reasoning of statistical inference remains the same, only the mechanics change. Okay, so here's a problem. Ashton thought that Genetic Cookies actually gave more chocolate chips than the name brand cookies. To investigate, she bought 10 bags of Chips Ahoy and 10 bags of Great Value, Walmart brand, and selected one cookie from each bag. Here are her results. Okay, so she did this 10 times for each bag. So she took a random cookie from each bag out of the 10 different bags. So the first question says to construct a 95% confidence interval. And does your interval provide convincing evidence that generic cookies have more chips? Okay, so I want you guys to work this one on your own as well as the second one. The second one, you're going to actually do a phantoms using two means. I will post the answers to these on Haiku, but please work together and try to do these on your own in class to see if you understand. Remember, it's just like the two proportion z-test, except it's applying the t-test. And this is what we did in class last week, the t-test. So use your critical... So for the confidence interval, we're going to use a t-star critical value. And over here, you want to use the t-test in your calculator to calculate this. Okay, so you can use examples that we did in class last week as well to go through this. But I will post the answers to this on Haiku. Please work together and try to get it right. And also make sure you study everything else that's on your syllabus because you will have a reading quiz when we return to class Thursday. So here's, I didn't finish this completely, but we will go through these Thursday. All right, thank you guys.